All right, so last Thursday we were talking about how to determine whether or not a sample contains a chiral compound in a lab setting, and we said that the thing you most commonly use is a polarimeter. And we said that chiral molecules rotate plane polarized light in one direction or another. And we looked at this with an example of a chiral compound, and we said one hand version of the molecules, let's say the R configuration, will rotate it in the positive configuration or positive direction, where the opposite enantiomer will rotate it in the negative direction. And so we said enantiomers are mirror images of one another that rotate plane polarized light in an equal magnitude but in opposite directions. And if you have a 50-50 mixture, then those rotations end up canceling out and you have no net optical rotation. All right, so now we have to get into a bit of math, which you thought you got away from. So let's describe optical rotation. Yep, it's going to be a lot of calculus here, so bear with me. I'm kidding. I hate calculus. All right, so the symbol for optical rotation is lowercase alpha in brackets. And then oftentimes, you'll see a number at the top and a little letter at the bottom. All right, so let's kind of break this down and describe the units for optical rotation. The units are pretty specific. It is degrees over concentration, and concentration is done in grams per milliliter, not molarity. Don't ask me why. And that is times your path length in decimeters. So the numerator is going to be the degree of that rotation of your plane polarized light. In your denominator, you've got your concentration times the path length. It's the only time I've ever seen decimeters used in practice. I don't know why they didn't use centimeters and why they didn't use meters, but it's just standard practice. So those are the units. All right, and then in the next part, we've got this number in the top right-hand corner. This is the temperature in Celsius that your sample is running. So your optical rotation may change depending on the temperature. Does anybody know why? Yeah, energy in the room, right? So molecules spin around depending on how warm the room is. If you've got a really hot sample, your molecules are going to move and vibrate faster. So you do have to account for temperature. And then this number down here is also pretty important. It's the source of your plane polarized light. So in this one, I don't know if you remember spectral lines from general chemistry. It's way back there, but this is the D line from a sodium lamp. So it's just one of those spectral lines that they isolate. They'll shine it through, polarize it into a planar fashion, and then shine it through your sample. All right, so kind of complicated. Like I said, though, it's your optical rotation times your concentration times your path length. So let's rewrite this. It's supposed to be concentration, not cone. Times your path length in decimeters. So sometimes what you can do is you're given the standard, so that's the alpha with all of your units factored in, and you might have an observed rotation, and from that you can actually extrapolate the concentration or something like that. This just becomes basically a big fancy algebra problem where you can solve for different variables. That is one of the sapling problems, I will warn you. It's just a lot of algebra. It's nothing super duper fancy, but if you get stuck on it, you can email me and I can try to provide you some hints. All right. So now, like we said, if you have a 50-50 mixture of enantiomers, you have no net optical rotation. No net optical rotation. What do we call that? It's a racemic mixture. I do. Racemic mixture. So now my next question is, well, what happens if we don't have exactly a 50-50 mixture? Well, we must observe some optical rotation, right? So let's kind of make some notes here. What happens if you have a non-50-50 mix of enantiomers? We already predicted that there will be optical rotation. Do you think it will be as high as the Pierce sample or a little bit less? It's got to be less, right? It's not going to enhance the optical rotation. It's going to be a lot lower usually. So what we do when we're looking at this is we calculate this as enantiomeric excess. That basically just means which enantiomer do you have more of than the other, and to what extent is it in a higher concentration? Is it twice as much? Is it 3 times as much? And so on. So let's figure out how to do this calculation. And oftentimes this is just abbreviated as EE%. It's just a lot easier to write that out. This is a bit weird. So your percent enantiomeric excess is your observed rotation for your mixture, specifically mixture of enantiomers, divided by your observed rotation for your pure enantiomer, whichever one you're investigating or the one you're trying to isolate, right? And then last but not least, you multiply this by 100. All right, so let's see this in practice and see what this really means. So a chemist has a mixture of enantiomers. The wanted enantiomer meaning the one you're trying to produce or isolate, has a observed rotation of plus 10 degrees. So we're going to assume that the temperature, everything else is going to be the same for both of our samples. Okay? The mixture produced, meaning the one we isolated in lab, has an alpha or observed rotation of 5 degrees. So first thing we're going to do is calculate the EE%. So hopefully we can do this without a calculator. So the observed rotation was 5 degrees divided by the rotation of the pure sample, which was 10 degrees, times 100, means we've got 50% enantiomeric excess. All right, so it is a bit weird to think about what this actually means. So let's break this down even further. So to break this down further, what I do is I say 100% minus my enantiomeric excess So if you subtract just 100%, or sorry, your enantiomeric excess from 100%, that leaves you with some number left over. What do you think this leftover number might be? Yeah, it might be your racemic mixture that's left over, right? So if you look at this one, this would be your leftover that is racemic. All right, so now my question for you. If 50% is left over and racemic, how much of our desired enantiomer did we actually make percentage-wise? 3/4, right? So enantiomeric excess is a bit confusing. You have to account for the fact that the remaining amount still contains some of your desired enantiomer, but it also is being canceled out by the opposite enantiomer. So let's think about this and write it down again. So we'll just say our desired was 50% plus half of 50%, because we know that that's racemic. That would give us a net of 75% correct enantiomer, or desired enantiomer. Does that make sense? 25% must be canceling out in some way, shape, or form, but that's not the stuff we want anyways. So it is kind of a weird numerical value. All right, so there are some tricky questions on sapling about this. Just try to not overthink them. A lot of them are just simple algebra problems and understanding what the concepts are for moving variables around. All right, so we're going to switch gears a little bit, and we're going to jump straight into isomerism today. This is one of the trickier subjects from this chapter, but I'll try to give you a flow chart. So before we start with our flow chart, let's redefine what an isomer is. Generic isomer. Anybody remember? Yeah, same formula. It's like the ultimate descriptor of an isomer. Okay, so let's start out our flowchart with just generic isomers. And we'll just write same molecular formula, just so we remember that. And then we're going to branch this out into different classes of isomers. The first class we actually saw, I think during our first week of class, where we had completely different structural connectivity, but same molecular formula. What do we call that? Constitutional isomers. Okay, and so these have a different connectivity. Do they have the same physical properties or different physical properties? Yeah, absolutely different. So in class we saw, depending on how they're structured, you actually can have a huge range of intermolecular forces. So maybe one H bonds and the other one doesn't, or something like that. So very, very different, easy to separate, purify, isolate, so on. So constitutional isomers are kind of cows and chickens. They're only similar in that they have the same atoms making them up. All right, stereoisomers are the hard ones. Stereoisomers have the same connectivity. However, they have a different 3D layout. So we've already seen an example of stereoisomers. Those were non-superimposable mirror images, right? So they had the exact same connectivity in space, meaning they were attached in the same way to some similar central atom, but they had a different 3D layout, and we could describe them as maybe being an R or an S. So for example, that was one type. What did we call those when they were non-superimposable mirror images? They're chiral, but specifically enantiomers. So enantiomers are very common in chemistry, and they are non-superimposable mirror images. and we've got potentially some different examples. So let's do one in blue over here. So this blue compound maybe has one wedge and one dash. So this would be 1,2-dimethyl cyclohexane in blue versus this one over here, which is also 1,2-dimethyl cyclohexane, but they're different, right? If we tried to assign stereochemistry to these, they would not be named the same compound. Do you want to try naming these really quick, just to confirm? Let's try it. Let's choose. Everyone's so enthusiastic. It's wonderful. All right, let's try the blue one. So for example, I'm just going to name this one carbon 1. Would that one be R or S? Highest priority be over here, right? Followed by 2, followed by 3. So it looks like we'd go clockwise around. Assumed hydrogen would be a dash, so this would be R. All right, let's do this one over here now. Is it? Go through and say 1, 2, 3. It looks like we're going clockwise, right? Or sorry, counterclockwise, but we have to flip it because our lowest priority would be an assumed hydrogen that's a wedge. So this one's actually also R. Okay, so if we went ahead and we named the blue one, it'd be 1R, 2R, and then we put that in parentheses, 1, 2 dimethyl cyclohexane. What about the red one? What do you think it's going to be if it's a mirror image? 1s2s. 1,2 dimethyl cyclohexane. It's usually pretty easy to spot enantiomers because if they have stereocenters, their enantiomer has the opposite stereocenters, right? So it's pretty easy to spot those, and we'll go over more practice examples later. All right, so enantiomers are pretty common. Like I said, if you have an equal mixture and you're testing for optical rotation, they cancel out. But if you have one by itself or one in excess over the other, they do have optical rotation. All right, the next one's kind of an offshoot that's a bit different. These are called diastereomers. Diastereomers are not mirror images, but have the same connectivity. Oop. All right, so let's take a look at a couple diastereomer types. So there's some that you may have seen already in your biology classes. We've got Sis Alkenes versus Trans Alkenes. These are connected in the same way, right? We've got a carbon-carbon double bond in the middle, but one's cis and one's trans. They are clearly not mirror images of one another, so these would be classified as diastereomers. So that's one example using alkenes. Let's look at another example using hydrocarbons. So we'll do the 1,2-dimethyl cyclohexane example. Oh, let me zoom over here. I'm running out of screen space. If we look at these two samples of 1,2-dimethyl cyclohexane, do you see how if we try to do the mirror plane down here, they're not true reflections of one another. They're connected in the same way, but they're not mirror images. These are diastereomers. Versus the one on the right, or sorry, the one on the left for enantiomers, these are true mirror images of one another, therefore they're enantiomers. Make sense? All right. So let's kind of classify these with a bit more detail. So constitutional isomers have different physical properties. Oop. They are easy to separate. All right, this is a bit different than enantiomers. Enantiomers have the same physical properties, they are hard to separate. I should say hard to purify. If you think about it, if they have the same physical properties, you can't distill them away from one another. You can't do any of the standard lab techniques that we've learned so far. They have the exact same solubility rules, they have the exact same boiling point, exact same melting point. So they're pretty challenging to purify, but we'll talk about techniques for doing so. The only way we can tell them apart is by the way they rotate plane polarized light. And I'll just write plane polarized light, PPL. That's the only way we can tell them apart. All right, diastereomers are different. Diastereomers have different physical properties. And they are easy to separate. I wouldn't go so far as to say they're easy to separate because they have a lot of the same properties, but they're ultimately quite different from one another. So they're not as easy to separate as constitutional isomers, but they have different boiling points, different melting points, different things like that. All right, so enantiomers are the tricky ones. They're the ones where if you go into medicinal chemistry, it's a bear to purify different enantiomers, and they spend a lot of time and money trying to figure out clever ways to do so. All right. So what I want to do today is a bit more practice on identifying different types of isomers. So I'll give you some practice problems. So what I want you to do is to draw all of the isomers for a following molecular formula and determine which of the isomers are chiral or achiral. And then if an isomer has a stereocenter designated as R or S, and then determine the relationship between all pairs of isomers. So let's do the following. We'll start out easy and then we'll go harder. So the first one is C3H7Br. So figure out all the isomers for that. And then if you fly through that one, I'll give you a second one. This is C4H9Br. So one more carbon. So I'll give you a little bit of time to work on this one. Yeah, C3H7. Yeah. It's my doctor handwriting. It's sloppy. Yeah. I'll rewrite it. I don't know if that looks better or worse, but it's 7-esque. All right, let's do the first one together, and I'll kind of walk you through how I come up with all the different enantiomers. We've got a 3-carbon chain. Is there any variation of making a 3-carbon chain? No. And bromine can only be attached with one bond. So we've got this 3-carbon chain. Maybe bromine's coming off that first carbon. So maybe this is an option. I'd say that works, right? All right, maybe it's coming off the second carbon. and maybe when it's coming off that second carbon, it's a wedge. Or maybe if it's coming off that second carbon, that bromine's coming off a dash position. Are these the same or different? Yeah, these are the exact same compounds. So you don't even need to draw that one if you don't want to. In fact, I'm just going to erase this and say it doesn't really matter because it's the exact same compound. Okay, what about if I have it off that last carbon? It's the same as the first one, right? So really we only have two different isomers here. All right, so the second bullet point said determine which of these isomers are chiral or achiral. Do you think the first one on the left is chiral? Let's determine that, right? So let's say we draw the mirror image down below. Are those the same compounds, the one above and below? Yeah, they're mirror images. I would name them both 1-bromopropane. So they're the exact same compound. If it's superimposable on the mirror image, meaning if the mirror image is the exact same thing, this must be achiral. All right, what about the second one? Is that chiral or achiral? Again, we can try doing the mirror image trick. We can say, all right, if we draw the mirror image of this, looks to me to be the exact same compound, therefore it's achiral. What was the other trick we used? Yeah, line of symmetry. This has a line of symmetry going straight down it, so therefore it must be achiral based on symmetry elements. Okay, so both of these are achiral compounds. We've identified that much. All right, and then it says if there is a stereocenter, designate it as RS. Oftentimes students will say, all right, there's a wedge coming off there. Is that a stereocenter? No, there's two methyl groups. So you can include dashes and wedges if you want. It doesn't automatically imply that there's a stereocenter. So no stereocenter in each of these. All right, now we need to determine the relationship between these two compounds. What's the relationship? They're isomers, same molecular formula. Constitutional isomers. So these are constitutional isomers. And they must have very different physical properties. We'd have no problem separating these if we wanted to. Yeah?
It's probably really obvious in this, but why don't we have to wedge or dash the first isomer?
Yeah, so that's a good question. For the first isomer, the question was, why didn't we include dashes or wedges? If there's no stereocenters, having dashes and wedges doesn't really tell you anything. It's just more work. So oftentimes they're completely omitted from molecules that don't have stereocenters. Yeah, great question. All right, so let's do the second one. We'll kind of do a similar thought process. We've got C4H9. So we've got 4 carbons now. This is going to make things a little bit different. So maybe we've got one option where it's 4 carbons and bromine's coming off that first one. That would work. Or maybe it's 4 carbons and bromine's coming off the second one as a wedge. I think that could work. Or maybe it's 4 carbons and that bromine is coming off as a dash. Are these the same compounds? Let's double check. Do they have the same name? No. Well, let's double check. They're both 2-bromobutane, but we need to designate their stereocenters. All right, the one on the left, is that R or S? R. Be R. All right, the one over here must be what then? S. So these are not the same compound. The one on the left is 2R, 2-bromobutane. The one on the right is 2S, 2-bromobutane. So they're differently named compounds. They must be different molecules. Yep. Yeah, they're enantiomers. They're non-superimposable mirror images. We'll come back and do all the relationships, though. All right, next question. What about this one? Whoops. We could do this, but it'd be the same, right? Let's really quickly identify that stereocenter. It would be R. This compound and this compound are the exact same compound, so we don't need to redraw it again if we don't want to, including the dash version. All right? And then same thing here. We already drew this one, so no need to draw it again. I'll just erase it. So it looks like we've got all of our straight chain carbon configurations. However, there's a few more. So maybe we've got 4 carbons arranged like this and a bromine coming off right there, right? That's still C4. So 4 carbons, 9 hydrogens with the bromine coming off. And then last but not least, maybe it would be this compound. So I think this is pretty much all of the possible isomers that I can come up for C4H9Br. So let's determine which ones are chiral. Is the first one chiral? No, it is not chiral. Just like we saw before, if you were to draw its mirror image, it'd be the exact same compound, have the exact same name. So this would be achiral. What about the second one? Be chiral for sure. If you draw the mirror image, it's not superimposable. Same thing with this one. What about the fourth one? I'd say achiral. If you drew its mirror image, it'd be the exact same compound with the exact same name. So this would be achiral. And what about the last one? I'd say achiral too. It would be superimposable on its mirror image. All right, so we've already designated the stereocenters that we have as R and S. Now we need to determine the relationship between the pairs of isomers. So let's do a handful of them. Relationship between these first set. Yeah, these are constitutional isomers. All right, relationship between the next set. Enantiomers, they are non-superimposable mirror images. And then all 3 of these must be what? Constitutional isomers. Do we have any diastereomers in this set at all? Yeah, I don't think so. Diastereomers, you have to have the same connectivity. The only ones that have the same connectivity we already classified as enantiomers, right? So they were mirror images of one another. We don't have diastereomers in this set. All right, let's do another one. I think we've got a few more minutes. This one I'm going to guide you a bit more. This one, 2-bromo, 3-chloro, butane. All right, so the name tells you a lot of information. We know that it's a straight chain butane. So it's got to be 4 carbons long. Bromine must be coming off of carbon 2. So maybe this bromine's a wedge. I'm just coming up with random ideas. And maybe the chlorine coming off of carbon 3 is also a wedge. So that's one possible option. All right, conversely, maybe the first bromine's a dash and the second chlorine's a wedge. Or maybe this bromine's a dash and this chlorine's a dash. Or maybe this bromine's a wedge and the chlorine is a dash. Or sorry, I didn't do that right. Chlorine's a dash. All right, so as far as I know, we've got 4 possible isomers going on here. All right, really quickly, let's identify stereochemistry. For this stereocenter, do you think it'll be R or S? Let's say R for that one. What about this one? Let's say R. All right, anytime bromine is coming off a wedge for that specific configuration, it must be an R. So we can quickly label that. Same thing with chlorine as a wedge. That would be an R. Conversely, what must this one be? S. It's flip-flopped. So we'll go ahead and label all of these. Same thing with this one. And this one as well. All right, so now we've labeled all of our stereocenters. Next question, which of these are chiral? Or we could ask the opposite question, which of these are not chiral? Do any of them have an internal plane of symmetry? No, I don't think so. And they have stereocenters. That means they all must be chiral. All right, now let's do relationships. So what's the relationship between the first two? They're the same connectivity, but are they mirror images? They're diastereomers. They're not mirror images. All right, next two. Are they mirror images? I don't think they're mirror images, right? So these would also be diastereomers. And what about the last set? I'd say they're not mirror images, so they've got to be diastereomers. All right, I will tell you though that there are enantiomers in here. Which ones? 1 and 3 you think are enantiomers? Perfect. All right, so I'm going to slide this down just so we have more room. And 2 and 4. Okay, so let's label our enantiomers. I see an enantiomeric set here. So these two are enantiomers. See how they're mirror images? The bromines were flipped and the chlorines were flipped. And then for 2 and 4, the bromines were flipped and the chlorines were flipped. So these are also enantiomers. Enantiomers have the same physical properties. Our diastereomers, if you had any set of diastereomers, they would have very different physical properties. All right, so tomorrow what we're going to do is we're going to do more isomerism practice. The problem of the day is a little bit tricky. What I will warn you about is when you're working on the problem of the day, try to draw both of them using the same 2D drawing and then compare them as 2D to 2D. It's really hard to compare 2D to chair. So try to make sure you're comparing apples to apples when you're doing that.